So, good morning. Welcome to Krishna's classroom. You know that today is a national day dedicated to the teachers, which is called the Teachers' Day. It also happens to be the birthday of a great philosopher, Dr. Sarvapalli Radhakrishnan, who was also the second president of independent India. Now, on this day, let me invoke the blessings of all my teachers who have contributed to making me what I am today. So, with these few words, let me come back to the topic. Today, I am going to talk about the problem of choosing measurable sets. Now, you know that usually what one does is the following. You have a non-empty or a set X with a measurable class of sets, or what forms a sigma algebra, and then you have a topological space with a topology designated by tau, and we will be working on mapping from X to Y, X to Y, which at the outset we would like to have these functions to be of a measurable class. Now we have already said what measurable class of functions are. Therefore, it all depends on, now you see, we are going to generalize the situation. See, when we worked with R, our objective was to generalize the concept of Riemann integral to a more complete form, and in the process we had to devise or extend the notion of distance from intervals to all possible subsets of the real line. In fact, we failed to do it for all possible subsets, but there were a large class of Lebesgue measurable sets, where the Lebesgue measure was in fact an extension of the concept of length of an interval, in the sense that whenever the subset, all intervals are measurable, whenever the subset is an interval, its measure turns out to be, the Lebesgue measure turns out to be the length of the interval. It's a very genuine, natural extension. And then we proceeded to the next step of developing degradation. Now we are in the process of generalizing all these ideas. Now you see, you have X. You're not making any special assumption of that. Now the collection B of subsets is what you call a sigma algebra, with certain properties which we have already explored. And then you have a topological space Y with a collection of sets along with it, designated by tau, which satisfy a certain set of properties, and the elements of tau are called the open sets. And we are generally working on mappings from X to Y. So, lot of versatility is possible. It depends, all depends on the choice of B, because we are not at the moment constrained by any desire to be it of the form. But a problem may arise where we would like the B to be chosen in a particular way and tau also to be chosen in a way. Quite often we'll be talking about what are called mappings from a measurable space to a metric space, or to be specific to R, C, or that is, we will be working on real valued functions or complex valued functions, or to Rn, which means a vector valued function, Rn or Cn, or even going beyond maybe some Banach spaces. So this is the direction in which things will. So this part will be decided by the class of functions you want to work on. On the other side, we would like to have a certain subsets to be measurable. That means those subsets should be in the measurable class of subsets. That is, should be elements of B. So B has to be constructed in such a way. How do we do that? This is the problem. Now let us, you will see more about this choice later. Now you see that this is done as follows. Suppose omega is a class of subsets of X. Omega is a class of subsets of X. That is, omega is contained in the power set of X. Some collection of the power set of X. In fact, the whole power set of X is a sigma algebra. So one can choose that, but that may not serve our purpose. Sometimes it is we may choose a sigma algebra which just fits into what we want to do. So that's what we are going to work. Now, from this choice, what we have, we would like omega choose the measurable class the sigma algebra. See, if omega already has a sigma algebra structure, that's fine, then you can choose that. But that may not be the case. So we would like to choose the measurable class that is a sigma algebra such that omega is a subcollection of such a sigma algebra. That is, if M star denotes the sigma algebra, that we arrive at. Then omega is a subcollection of m star, which is a subcollection of, but this may not be a sigma algebra, but this is a sigma algebra, and Px is the power set of x. Yeah, so this is the point. And we would like to do it optimally. Optimally in the sense that we want to work with the just bare minimum of subsets of x, which will form a sigma algebra and at the same time contain omega. Is a sigma algebra. So how do we do this? First of all, we observe that given omega, I'm talking about a non-empty connection. Given omega, there exists several sigma algebras containing them. First question that you ask is, does there exist such a sigma algebra? In fact, Px is a sigma algebra containing now we in fact choose, so you are assured that there is at least one sigma algebra which satisfies our criteria. Now we want an optimal one. So how do we choose? We choose the minimal class in some way, having this property. So how do we make the choice? What we do is we look at all the sigma algebras which contain omega. Okay. Now we choose the intersection of this class and ask the following question: is this a sigma algebra? If that is a sigma algebra, that is a minimal sigma algebra, because we have already accounted for all the sigma algebras containing omega. And if you take the intersection of this class, it will become the minimal class. So this is our strategy. In fact, it works. Okay. So we have the following theorem. Let me just change the notation. I want to use omega for some other purpose. let me use F here. Then wherever I have written omega, I'll write F. And then I have this property, namely F is a collection of subsets that is given. Okay. In fact, Ex is a sigma algebra containing. So I just change the notation slightly, and that should not cause any problem. So if F is a collection of subsets of X, there exists a smallest sigma algebra M star X such that the collection F contained in so what it says is that if F is a collection of subsets of X, then there exists a smallest sigma algebra that is unique, therefore, say M star in X such that F is contained in star. So this is the theorem that I'm going to. Okay, I have already given the strategy and it's very easy to do. So let omega designate. I wanted to use omega for this purpose. The set of all M, where M is a sigma algebra in X containing the given collection. So let omega denote the set of all sigma algebras on X, which will contain the given subcollection. Okay. Now we define intersection of all M where M belongs to omega. That means we are picking the common subsets of all these sigma algebras and put them together and call that M star. That is our definition. Now, we want to investigate whether this is a sigma algebra. If it does, then everything is done. So we claim it's a sigma algebra. How do you prove that? What are the things that you have to show? First thing we have to check is that x belongs to. So x belongs to M for every M. Because M is a sigma algebra. Okay, which implies M star, which is the intersection of all such M's. Okay, so the first part, that is x belongs to M star, is verified. The second property that we need is this: if A belongs to M star, then A complement belongs to. This is what we want to. How do we prove this? See, A belongs to contained in omega. Okay? Sorry. Belonging to now, this implies A belongs to M for every M belonging to M for every M belonging to omega, and therefore and since M is a sigma algebra, A complement belongs to. Which implies A complement belongs to M star, which is the intersection of all these M's. Okay, so that completes the proof. Now the third one is, in a similar way one can prove it. That is, if An is a subcollection of M, it's a countable subcollection. For every M omega, then what we can infer is this: union because M is a sigma algebra, which implies union n equal to 1 to n belongs to m star, which is the intersection of all these. Okay. Therefore, you see that it is closed with respect to countable union. Then there are other consequences would follow. That means the empty set is an element of M star because X is in M star, so its complement is in M star. And then the intersection of all elements of M star is also an element of M star. That also follows the same way. Okay, by taking the complementation. Okay, so that completes the proof of this theorem. And you see that this is the smallest sigma algebra that contains the given. So M star is the collection of sets F, unique therefore, unique. So what we have proved is that given F, there is a uniquely determined sigma algebra, which is the smallest sigma algebra containing set of elements. So for our purpose, since we will be focusing on what happens to these sets in F, to work with, we would need the smallest sigma algebra that contains F. And that is what we have shown, that there exists such a sigma algebra. Okay, let us look at some of the consequences. Now recall the following result. Suppose you have two topological spaces . Then we can talk about continuous functions. It's a large class of functions. So f from x to y is continuous if f inverse of v belonging to, that means these are all the open sets that we have designated in Y. These are all the open sets that we have designated in X. It means every open set in Y should be pulled back, or the pullback of every open set in Y should be an open set in X. This is the scenario. We have X . You suppose this is an element of V is an element of tau Y, that means it is open in Y. Then you would go for the pullback of this. So there is the function f. So you go to the set which is what you call f inverse of Y. Sorry, f inverse of V. F inverse of V consists of all those elements in X which will get mapped into different definition. We want f inverse of V to be an element of tau x. That means it is designated as an open set in our new in the topological space x dx. Okay, so this is what you require for f to be continuous. So this is so you see, continuous functions are a large class of functions, and quite often when we develop the integration theory, we would like all the continuous functions to be amenable to our purpose. Okay, so what is that we would require? First of all, this function or x should have a sigma algebra on it. Secondly, the function f should be a measurable function. Then only you can develop the integration of that. Okay, so there are two requirements. Now, to do integration, on f, we would require you would require a sigma algebra on x say m such that xm should be a measurable space and for the continuous f, f inverse of b, f inverse of b should belong to m for every v in tau 1. This is what is needed. So what we need to have a designate some subsets as measurable class, and we would like the pullback of all these open sets in Y to be measurable. Okay, so that they should be, after all, they are all continuous functions. Sorry, they are all elements of, since f is continuous, f inverse of b, therefore we require the smallest sigma algebra on x which contains tau x. So tau x should be a subcollection of f. That is every element of tau x should be an element of M. And how do we get that? So we get that, we choose the so we choose the all sigma algebras containing therefore what we have now, first of all you see that if you carefully examine the definition of open sets and the measurable class of sets. Now you see that in the case of measurable class of sets, if A belongs to is measurable, then A complement is measurable. Whereas in the definition of the topology, if A is open, it does not imply A complement is open. Okay, so that is not there, right? And there are more intricacies about it. Topology is closed under arbitrary union and finite intersection, whereas the measurable class or the sigma algebra is a collection of sets which is closed under countable unions and countable intersections. Now these are all the differences that you see. The only common element that you have is x is in M, x is also in tau x, and x complement is in tau x, and the empty set is also designated as open in tau x. Okay, so you have only those two properties are the same, but the others are different. Therefore, essentially, tau x is different from the minimal class of or minimal sigma algebra that you construct from I mean in general construct from tau x. Okay, so that is the construction of this, and you see that once you do that, so once you do that, you see you have two things now, x, tau x, this is a topological space, and x, this is a measurable space, and you have y, which is a topological space, and you are talking about mapping from here to here, which is also mapping from here to here. Now you clearly see that when you take an open set here and pull it back, it is going to be in tau x, but tau x, every element of tau x is an element of M, therefore it is in M. Therefore, all continuous functions from x to y are measurable. All continuous. Now this is something that you have. So now you have two structures on X. You have a topology on that, and the measure generated by, you can call that the measure generated by, the measurable sets generated by the topology. So M is the measurable, the sigma algebra generated by on X. Which assures you that all continuous functions from X to Y are now also measurable. So you can comfortably talk about the integration theory when we come to that. Okay. Now this collection is given a name. These are called Borel sets. Borel sigma alpha, Borel sigma alpha. The special topology on means every open set in X is now an element of M. So this is the speciality. This is the minimal class of such case, and we give it a name. It's called the Borel sigma algebra. That assures that all continuous functions are measurable. So that means a large class of functions from X to Y are now measurable, and that is the least minimum that we are asking for. And in fact, much more happens here. Okay. Now, M is not the whole of tau X. So, what is the structure of M? This is what we want. Which sets belong to? This is the question that we are asking. Obviously, all open sets are. And what more? The complement of open sets are also in the complement of all the closed sets. That contains all the open sets, all the closed sets. What more? Should be the obviously finite union of closed sets is closed, and therefore it is there. Finite union of open sets. Okay, finite union of closed sets is closed, and therefore it is certainly in M. you see that finite intersection of open sets is in M because that is open. But now what additional thing that you get is this countable union of closed sets. This may not be in the topology. Countable intersection of open sets. So M is closed with respect to countable union of closed sets and countable intersection of open sets. Now these sets are given a name, what are called F sigma, and this collection is called G delta. Okay. G is for geoffnet, that is open in German word for open, and delta is Durchschnitt, that means it is the intersection. Whereas sigma stands for sum and F stands for usually designates what are called closed sets. I have forgotten the exact word which is designated, but it again comes from German. Okay. So sigma stands for summation, and delta stands for Durchschnitt, that is the intersection. Okay, so you have these two representations. Now, stretching this, you see that F sigma sigma or G delta delta and all sorts of combination, F sigma delta, G delta sigma, etc., etc. They are all now going to be elements of this. So it is going to be a much larger than, so hence much larger than the topology on X, that is, so it's a huge class. Okay, very comfortably you can work on that. But that happens to be the smallest sigma algebra that you can get containing this tau x. So we often superimpose on X given a topological structure. You often superimpose on X a sigma algebra, which is the smallest sigma algebra that contains tau x. This is the strategy, and this is called the Borel class of or Borel sigma algebra. Okay, so whenever you say just Borel sigma algebra, it is taken for granted that on X, suppose you say M is a Borel sigma algebra on X, then it is straight away implies that X has already a topology on it, and this is the sigma algebra that contains this particular topology. So that now the advantage that you have is this: there is a huge class of functions, namely all the continuous functions from X to Y are now measurable functions. Therefore, one can comfortably work on them to develop an integration theory. Okay, so that's what I want to say. So what we have is the following. Suppose is Borel measure. What does it mean? It means you have got X, tau X is there, then you have X, this is the measure space, and then you have got Y, tau Y. We are talking about mappings from here to here. Okay? What do you mean by Borel measurable? That is F inverse of V is an element of M for every belonging to tau Y. This is the condition. For every element of every open set in Y as designated by tau Y, its inverse image in X is in the sigma algebra. Then you say it is Borel. Okay. So you can see the interplay of the two structures on X, namely the topological structure and the measure and the structure of the measurable class, sigma algebra structure, which are chosen in such a way that they get along well. There is no conflict between them, so that at least all continuous functions belong. Now, this means more functions than continuous functions which are measurable. So we are not just working on continuous functions alone, but on a larger class of functions. And this larger class of functions contain all continuous functions. Okay, that's what I mean. So Borel measurable mappings are called Borel functions. Now you see that it's actually the preoccupation of analysts that there should be some topology on the domain and on the range, so that you are working on what are called continuous functions. But this is not necessary. There are situations. I mean, this is you see the versatility of this. The situation is this. Suppose you are given any subcollection in X, not necessarily with any structure, you can find a sigma algebra which contains it, or a minimal sigma algebra which contains it. And then you can talk about what are called measurable functions. Okay. So in a wider scenario, one can make use of these ideas. For example, in the probability situations or spaces, one can make use of this, where at the outset there may not be any topology unless you impose one. Okay, you can choose the collection of subsets in such a way that it serves your purpose. Okay, so let me wind up the day with this small topic, but I hope everyone got an idea of why you need to choose a minimal class of sets forming a sigma algebra on the domain. Okay. So thank you very much. Once again, wish you all a very happy Teachers' Day.